Hello, good evening all for this course. This is live session 5 of the course Solar Energy Engineering and Technology. So, this course is taught by Professor Pankaj Kalita and I am Rohit. I am a PMS scholar at IIT Bombay. I will be taking this live session. So, basically, this live session is to increase the interaction between students and the course. So if you have any doubts or anything related to concept that they discuss in the अरे यार, sorry, the microphone was off. Okay. So good evening everyone. Once again welcome you all to this live session 4 of this course Solar Energy Engineering and Technology. The course is taught by Professor Pankaj Kalita and I am Rohit. I will be taking this live session. I am a PMRF scholar at IIT Bombay. So, how I planned this live session is that we will first discuss the different concepts. We'll go through the lecture slides and discuss the different important concepts that will help you in solving the assignment problems. Apart from that, um, I have some assignment problems, so I will solve all those assignment problems from the previous run of the course. And these the assignment problem which I will solve here is from the previous run of this course, not from the current course, because we have been refrained from discussing the current assignment problem, so that parity is maintained between all the students. Okay, so don't worry, the assignment problems are not too hard. It's straightforward. You just have to learn the concepts, and those assignment problem can be solved very easily. Okay. So even if there is anything you want to discuss or any concepts which is not so clear to you, so we'll discuss that. Okay. So first, what I will do, I will discuss the concepts that are being taught in this week 4. So that will help you familiarize with the concepts also. Apart from that, I will go to the assignments problem after that. Okay. And so let's start. I think everyone is here and it's already 7:17. So yeah, I think Sankar has some problem with assignment questions. So don't worry, don't panic. We will solve those assignment questions. We'll solve similar type of question that will help you to solve these current assignment questions also. Okay. And if there are any queries in between, so you can ask in between the lecture also. And if you want, you can also put those queries in the white box here, so I can see those queries and I will answer in intermediate time. Okay. So let's move to the slides. Okay, the first lecture was basically lecture 9 of module 4, which basically discuss about the solar photovoltaic. So, but you have, do you guys have any idea about what solar photovoltaic is? Anyone from you have any idea what solar photovoltaic is? Shankar, Suruchi, Rajeshwari, am I audible to you all? Am I audible to all? Okay, Rajeshwari is saying yes. Okay, so do you guys have any idea about what a solar photovoltaic is? Any basic idea like what it does? Okay, so I assume that you guys have don't have a basic idea about solar photovoltaic. So don't worry, I will discuss from basic to we will go into the science behind those solar photovoltaics also. So I will try to explain it very beautifully and in basic words so that you guys can say that, yeah, I know solar photovoltaic. Okay. Somebody wants to join. Venkatesh wants to join. Okay, so let's move. Let me see. Yeah, it's recording. Okay, so basically, solar photovoltaic is something you see it consists of two words, and not only two words, it is basically it consists of three words. Let's see how it has three words. First word is solar, that means something related to sun. Okay, another word is photo, that means something which is related to light. Third word, third word is voltaic, which is something related to voltage or electricity. Okay, so that's how this word solar photovoltaic is coined. So when you hear this word solar photovoltaic, it means converting light into voltage, converting the light coming from sun to voltage using different energy conversion devices. So what are energy conversion devices? Energy conversion devices are those devices which takes one form of input and then convert it to another form of output energy. So input can be solar. Solar is also a form of energy. Chemical, mechanical, kinetic, potential, any type of energy, and then it converts to electricity, heat, anything, rotational energy. Okay, so these devices are actually fit into a broad area of energy conversion efficiency. Just keep me a minute. Okay, so those who joined just now, so we are actually discussing the concepts of solar photovoltaic. So solar photovoltaic are energy conversion devices that takes energy from sun in the form of light and then it converts it to electricity. Okay, so it converts directly to electricity. No intermediate conversion steps are there. Now, so here he has given a very good definition of solar photovoltaic, that is basics of PV cell, its construction, manufacturing, working principle is discussed here. So if we see the solar photovoltaic conversion, let me take a laser pointer here. The devices that are used for PV conversion, PV is basically a short form for photovoltaic. It's called solar cell. When solar radiation fall on these devices, it is converted directly into DC electricity. Okay, so there can be a question here: कि solar photovoltaic conversion devices converts light into AC or DC electricity. So what will be the correct answer? The correct answer will be DC electricity, that is direct current. So it will be something like, if I draw it, so it will be like this. Okay, not fluctuating like AC. Okay, not like this. This is not. This is okay. And what are the major advantages of using solar photovoltaic conversion devices? So there are no moving parts. You don't have any moving parts here. Just the solar cell is there, light is impedant on it, and then it converts it to electricity. Requires less maintenance. Yeah, it requires less maintenance because there is no moving parts. Simple thing. It only maintenance required is you need dusting, you need to take care that any cell is damaged, you need to replace it. That's all. And maybe some glitch, maybe in the electrical circuits, or maybe otherwise it doesn't require a very high maintenance. Work quite satisfactorily with beam or diffuse radiation. So in the previous lecture we have discussed about this beam and diffuse radiation. So yeah, these devices can work with both of the radiation. Okay, adopted for varying power requirements. Yeah, the cells are available in various sizes, so don't worry about this. There will be cell for even the calculator has a very small solar cell. Okay, so you can see the scale of the production. What can be limitation of this PV conversion? First thing is that efficiency is very low. So this is a major factor. Efficiency is very low compared to a, like if you see a very advanced coal power plant, we have efficiency as high as 40-44% something. And if you take a normal solar photovoltaic conversion cell, then efficiency is something around, at max it will go 20-22%. So efficiency is almost half of coal power plant. So you can see why these solar cells are still not getting penetrated into society despite the benefit it contains. Okay, another thing is that solar energy itself is intermittent. So you, when you have clouds you don't have sun, when you have rain you don't have sun, in the night you don't have sun. So at that time where do you get the electricity? You need your fan to be running every time in the summer na. So it doesn't mean that there are clouds, okay, so there are clouds, no electricity, it cannot be tolerated. You have to have some specific criteria, specific storage systems, so that these devices can be utilized for different specific purposes. Okay, third thing is cost, very costly. Okay, so in India government actually gives a lot of subsidy, that's why the solar cell are comparatively cheaper, but even after so much of subsidy these solar cells are quite costly. Okay, but with new technologies coming in and market forces playing their role, the prices of these technologies are quite low now, getting low now. Okay, so earlier, like 1 decade earlier, these solar cells was beyond the reach of a common man. But in these days, most of the people have these type of solar systems installed on their roof. And there is a fact here. It's like 90% of the current commercial production of solar cells are single crystal or multi-crystal range silicon cells. Okay, so 90% are these. So what are these? We will study in the future slides. So as of now, you can take this as a fact that 90% are silicon-based cell, which are single crystal, monocrystalline or multi-crystalline, polycrystalline, you say. These are the various applications. I don't think I need to go into detailed into these things, like what are these applications. Now if we see the development of this photovoltaic through a milestone, like how it got developed through the different timelines, and who are the scientists or researchers who are behind these type of discoveries of these solar photovoltaic cells. So 1839, the first time the discovery of photovoltaic effect was done. So actually people credit Albert Einstein for this photovoltaic effect discovery, but he didn't discover it. Albert Einstein explained the photovoltaic effect. That's why he got the Nobel. Okay, so it was Edmund Becquerel who discovered the photovoltaic effect. Photovoltaic effect is that when any material or metal is exposed to light, so it generates free electrons, and type of current it generates. So actually Edmund Becquerel discovered it, but he didn't knew that he didn't explain it why this current is coming, what is the reason behind it. Albert Einstein explained it, how these things, photoelectric effect, through his very famous published paper of photoelectric effect. Okay. Yeah. So you okay, so I will move to the problems. So let's move to the problems. So okay, so for problems to be discussed, you need to learn the concepts. Okay, so the first, like if you see this problem, like problem based on material band gap, so you must be getting some problems on this band gap type of things. Okay, so I will not discuss band gap, as you said that you want to discuss problems only, but for knowing the problems, to solve the problems, you need to know what are the band gaps. So I must suggest you guys to, who is this joining? I must suggest you guys to go through this theory in a better way, so that you can understand what is the main what the problem asking, what is being asked in the problem. Okay, so let's say you need to calculate the band gap, okay, with variation with the temperature. So this formula is to be used. Okay, egt equal to eg0, that is eg naught, minus at square upon t plus b, where t is basically the temperature and a and b are constant, that is given for different type of materials. So from this table you can get the value of a and b for different materials like silicon, germanium and gallium arsenide is given here. And at t equal to 0, basically this egt equal to eg0, so this term becomes 0. How? You just put t equal to 0 here. Okay, so we will take this equation and we will solve a problem now. Okay, so you need to calculate the band gap energy in a silicon crystal at 50 degrees Celsius, 1.1 electron volt. Okay, so if there is a band gap energy that is to be calculated at 50 degrees Celsius, so just recall the formula. The formula is 50 EGT at 50 degrees Celsius. Okay, and okay, so it should not be, T should be in Kelvin. So it will be not 50 degrees Celsius, it will be 323 Kelvin. So you guys know the difference between Kelvin and Celsius. So always use, I think I should edit it. Kelvin is 273 plus 15, 323. Okay, so EGT equal to 323. Now you need to know the value of EG0. So for what was the question? For silicon crystal. Okay, so go to the table, silicon crystal. What is the value of EG0? 1.166. Minus, what is the value of A for silicon? It's 7. Into, what is the value of T? 323 square. Sorry, it's not this. upon 323 plus, what is the value of B? 636. Now calculate it. So 323 square into 7 divided by 323 plus 636. Now you need to subtract this value from 1.166. It is coming around point 0.4. Okay. Okay, this thing we missed. 10 to the power minus 4. So 323 square into 0.0007 by 323 plus 636. Yeah, it's coming around 1.166 minus 0.76. So this will be around 1.089 EV. Okay, so this is the correct answer. So let's see. Yeah, something they have rounded it to 1.1 electron volt. Okay, so question like this will be, you will be able to solve. Rajeshwari, will you able to solve question like this? Yes, sir. Okay, so let me give you a question then. Let me give you a question so you guys should practice. I want you guys to practice questions. Okay, so let's say I remove everything here and I write a question here. And the question is based on this. So band gap energy in silicon at 50 degrees Celsius. Okay, so let me copy this table. I copied this table here. Now I wanted to ask you guys, calculate the band gap energy of gallium arsenide at 70 degrees C. Okay, do you need the formula also? Should I copy the formula? So let me copy this formula also. Now faster, solve this question fast. Okay, keep practicing. When you practice these type of question, and these questions are pretty straightforward. I don't know why you guys are getting anxious about these questions. So don't worry. These when you practice more question, you will be easily able to solve these type of questions. Okay. So other two questions are also there. We will discuss that also. Okay. So apart from that, two questions are there. I will change the values here. Okay. So these questions are already discussed. I will change the values and then we will calculate the answer. So anyone has calculated? So what I will do, I am putting this slide on here. So you guys please calculate and I will giving you like it's 7:40 now. Let's say I will give you 5 minutes. Calculate and say how much is the answer. Then I will show you the correct answer. In fact, I will calculate you this question in front of you itself. Okay, so Nisit has calculated it as 1.394. So let's see whether this is correct or not. Rajeshwari, Sankar, have you calculated the values? It's okay. Even if you are doing it wrong, don't worry. Just try the question. The more question will try you will try, the more you guys you will be able to solve the assignment problems. So assignment problems are not so difficult as you are thinking. I am sure that there must be one problem on band gap, and if you will try, you can easily solve it. Okay. So let's solve this question. Coding. Okay. Okay, let me take the pen. So what it is requiring to calculate EGT. So if you want to calculate this value of EGT, then you need to know the value of EG0 and A and B and T, 70 degrees Celsius. So the first thing you need to approach this question is to convert 70 to Kelvin. Okay, so you take 70 plus 273. So how much it will be? 343. Okay. And for gallium arsenide, what is the value of Eg0? It's 1.519 minus, okay. What is the value of A? 5.8 into how much is the value of T? 343 whole square, 343 plus how much is the value of B? It's 204. And another thing is that it's not 5.8, it's 5.8 into 10 to the power minus 4. So mind it. Now you take the calculator, it will be 1.519 minus 5.8 into 10 to the power minus 4 into 343 whole square divided upon 343 plus 204. It comes out to be around 0.124. So subtracting it from 1.519, the answer is 1.394. That means the answer got by Nishit, was it Nishit, is correct. Sir, I could not post any message in discussion forum. Can you show the chats from discussion forum? Should I show you the chats? Okay. Were you guys able to solve this question? Like the question which I gave you? Is it okay if any type of question is asked in the exam or in the assignments by changing the values or changing the wordings, where you will guys will be able to do it? Okay, just go to course. So, Sankar, I am going to the discussion forum, showing this discussion forum. Please see. Okay. So this is the discussion forum. Ask a question. So you see, people have already asked these type of questions like detailed solution to assignments. Similarly, you can go here, click here new conversation, and you can put the question here. Okay. So like the benefit will be that ki whatever question you will be asking here, so everybody who is part of this course will be benefited from the answer of this. Okay. It will shall be very helpful if you update the detailed solution of the assignments. It will be really helpful if you do it every week. Please share it. Then see. So there are course TAs for this course who basically looks after this discussion forum thing and answer it. So any questions related to this live interaction session, if you post it any question regarding live interaction session, we will answer it. Okay. And apart from that, this is problem solving session. So if you guys are not able to participate in any of the problem solving session, so the recordings are here. These are my recordings, these are Soumya's recordings, so you can refer to any of these recordings. Okay. So you just have to click these recordings and you will go to the YouTube channel that contains basically the live interaction sessions. Okay. So you guys can also, those who are not able to participate can easily go through the live interaction session and cover the course also, like get the knowledge of the whatever is discussed in the live interaction session. Apart from that, the slides which we discuss basically are uploaded here also week wise. So don't forget to see these slides. These are very important slides and these contain questions from previous run of the assignments and we solve these questions in front of you. Apart from that, we also discuss some concepts also. Basically, I always try to discuss some concepts because without concepts you won't be able to go deep into the question. You won't be able to understand the question. Don't try the question without seeing the videos and lectures. When you see the videos and lectures, you will be able to relate yourself with the data or question that is being asked. Okay. So I think that is okay. Okay, so Shankar is saying ki I think okay. So don't worry, it's very easy. Just keep trying, keep pushing yourself. You will be able to solve it. Don't be frustrated or I think you guys are very smart and you will be able to do it. Otherwise, we are there to help you always. Okay. So next question. Let's solve our next question. Are you guys ready? So let's see what is the next question. The optimum wavelength of the light of photovoltaic generation in the silicon cell is this. Okay. So this is pretty straightforward question, but still I will give you guys here. Let's move it here. Okay. So the optimum wavelength. This is in micrometer. Okay. This is micrometer. I think I have. No micrometer symbol here. So, as of now, please assume it as micrometer. Okay. and you need to calculate what? The optimum wavelength. You have to calculate the optimum wavelength, and the formula is here. So let me change the values. So everything is here. I don't want you guys to copy, so I am changing these values. I am making it 1.84. So now calculate the optimum wavelength. So what does this optimum wavelength mean? What does this optimum wavelength mean actually? Why we are requiring an optimum wavelength? Why do we want to know optimum wavelength for photovoltaic generation in a silicon cell? So I will tell you what happens actually. So these are basically semiconductors. So these have different properties associated with these semiconductors. And when you have some different properties, so it will be requiring a specific wavelength to generate a maximum or a optimum amount of energy. So that is optimum wavelength for that type of cell. Okay. So this is given by E, that is energy, equal to 1.24 upon lambda. Lambda is wavelength. Okay. So if you shift lambda here, E here, and put the values, so you will be able to get the optimum wavelength. So earlier it was 1.11, just put it here 1.24 upon 1.84 and you will get the value. Okay, so let's focus it for 1 minute and let me see who is able to calculate the values. So be fast. Can anyone do it? Let me show you the question. Then we will discuss the last question, then we will have a break for 5 minutes. Okay. So you guys are not getting bored of the question which I am bombarding to you. But these are pretty straightforward question, I must say. So no need to panic. Huh, yeah. Who is this? In this question. Okay. Huh, yeah, say. Uh-huh. Okay. E is band gap energy, I think. And this is not micrometer. This is band gap, EV. Okay. So yeah, I was confused actually. Okay. So I changed this question. Is it the same? Did I change the question? Oh, they have also given it wrong. No, oh, they have actually calculated it. Okay. And can anyone say how is this value 1.24 coming? So let's say there is a formula E equal to 1.24 upon lambda. How is this 1.24 coming? Why is it 1.24? Why it is not 1.42 or something? Sure. This is the correct answer. It's a multiplication of Planck's constant and the speed of light. Nishit has already calculated it as 0.6739. So I assume, okay, Rajeshwari has also done it. Very good, Rajeshwari. Very good, Nishit. So yeah, most probably these values are quite nearby. 0.674 and 0.6739 are same. C has actually rounded it up. So I think this is the correct answer. Okay. And do you want to go for this third question? I think third question is also same. Calculate the optimum band length of light for photovoltaic generation in a CDS cell. So band gap is given. So it's very easy. You can calculate the optimum wavelength for that. So one thing I want to focus here. So let's see. In the previous question, we have calculated the optimum wavelength of light for photovoltaic generation in a silicon cell. Okay, and what it is 1.12 micrometer for silicon cell. But for cadmium CDS cell, cadmium sulfide cell, it is 0.512 micrometer. Okay, so it is almost half. And the other thing is that the band gap is also actually changed here actually. So here the band gap was 1.11 and here the band gap is 2.42. So the band gap has actually band gap is directly related with the material that is used for solar photovoltaic, and depending on the band gap we get the optimum wavelength value. Okay, so I think all these type of question, even if we change the wordings or the wordings are changed or some values are different, you guys will be easily able to calculate these type of questions. Okay, so let's focus on this, and if there are any questions, please put it in the white box and let's have a break of 5 minutes. So, and in the break, please go through the different slides which we discussed here or the different questions. And if there is anything you need to ask from whatever we discussed till now in this live session, please feel free to ask. Okay. Okay, so I think you guys have a break and anything you wanted to ask in between? Nothing? Okay, so then let's discuss the future questions. So no questions here, no questions here. I want that more and more problems can be solved in this live session, so you guys can have a confidence when you try to solve those type of questions. Okay, so it's all about the way you practice. The more you practice, the more you will get to answer these type of questions. Okay, silicon, silicon, silicon. So yeah, there can be question on this. Okay, so please remember this. These two formulas are there, na? So there can be a question on this, like Fermi energy level of an N-type material. How do you calculate it? And Fermi energy level of a P-type material. Okay. So these formulas are there. EF equal to EC minus K into T. What is K? K is basically a Boltzmann constant. Okay. T is the temperature, and temperature is in Kelvin, not degrees Celsius. Okay. NC and ND are basically effective densities of state in conduction band, and D is for donor concentration. Mm, yeah, okay. So this is a very big question. So I think this question is what you wanted to solve. So let me solve this question actually for you. I will take this question from here and I will try to solve it there itself. So I think most of the questions here have been discussed. Let me solve this question from here. You guys also try to solve this question, okay? So you guys can have a good understanding of how to solve this question. So it is basically saying the question, first you try to read the question, what the question is saying. The question is saying a p-type silicon, so it's a p-type silicon, okay, has effective density of states in the valence band as 1 into 10 to the power 22 per centimeter cube. So effective density is given. An impurity from third group, okay, so it's a trivalent semiconductor, so impurity is added. So impurity from third group with concentration of 1 into 10 power 19 per centimeter cube is added if the band gap, so band gap is also given from the closeness of Fermi level with valence band at the temperature of 27 degrees Celsius. So first thing what you will do here, first thing is that you will, the first thing you will do is to get the formula, but before getting the formula, convert the temperature to Kelvin. Okay, copy the formula. What was the formula here? So let's copy it from here. So it was a p-type semiconductors. Can we copy this formula? Edit. Okay, so let's copy this formula from here. So it was p-type silicon semiconductors, so this formula will be applicable here. Okay. Now in this formula you will see you need the value of K, which is given 8.62 into 10 to the power minus 5 electron volt per Kelvin. So this is minded, this is Boltzmann constant, but the units are electron volt per Kelvin. So if you want to write it in joule per Kelvin, so Boltzmann constant is 1.38 into 10 to the power minus 23, because 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. Okay, and T we have calculated as 27 plus 300 equal to 27 plus 273 equal to 300. NV, you know, NV, the value of NB 1 into 10 to the power 22, and value of Na, you know, 1 into 10 to the power minus 10 to the power 19. So everything is given, you just have to calculate EF minus EV, that is what being asked here. Okay, so let's calculate it. So first thing it is saying ki if band gap of silicon is 1.1 electron volt, find the closeness of the Fermi level with the valence band. So it's saying that if the band gap of silicon is 1.1 volt, so if there is a Fermi level, so find the closeness with the valence band at a temperature of 27 degrees Celsius. So closeness is basically it is saying difference. Okay, how much is the value of K? The value of K was there. The value of K was 8.629 into 10 to the power minus 5. How much is the T? T is 300. How much is the NV? NV is basically the effective density of states in the valence band. That is 1 into 10 to the power 22 per centimeter cube. So if the upper unit is per centimeter cube, then the units of below term should also be per centimeter cube. If it is not in per centimeter cube, then you have to change it to per centimeter cube. Okay, so everything is there, and this is ln. Okay, after you put everything, just calculate it. So it comes out to be around 0.178 or something. Okay, electron volt. So this is the correct answer. So if you have any queries, please feel free to ask for this question. Let me see if anybody has any queries. Okay, Riz. Okay, so feel free to ask if you have any queries. Okay. Otherwise, please see this question. I have erased the answers. Try to solve it by yourself. And let me change. Let me change. Take this as, instead of 1 into 10 to the power 22, take it as 5 into 10 to the power 23, and take it as 2.8 into 10 to the power 20. So everything is same. Take the temperature as 32 degrees Celsius. Now calculate the same question, calculate. Okay, calculate it. Okay, so Nishit has calculated it as 0.19706. Okay, so I think this must be correct. Okay, so now let us discuss the previous run assignment questions. We have discussed enough of these type of questions, and I'm pretty sure that you guys will be able to do it pretty easily. Okay, so one thing is, let me make it clear that these questions are not from current assignments. These are from previous run of this course. Like this course was also run in the last year. So these assignment questions are from that run of the courses. So yeah, see the first question here. The optimum wavelength of light for photovoltaic generation in a cadmium sulfide cell having a band gap of 2.42. So I think let's do it. This is a question which we solved also. E equal to, it was something now 1.24 upon lambda. So we need to calculate lambda equal to 1.24 upon 2.42. So it's 1.24 upon 2.4, something around half. So it should be around zero point 0.5 or something. Okay, micrometer. So what is the version? This is the correct answer. 0.512. Okay. So see if you guys are able to do it. Try to do it. Okay, so let's move to the next question. So next question is asking silicon crystal is doped with an impurity of fifth group, that is pentavalent, with concentration 10 to the power 15. The effective density of states in the conduction band is this. Boltzmann constant is also given if the band gap, this is not gas, this is gap, for silicon is 1.1 electron volt. The shift of Fermi energy level with the conduction band at the temperature 27 degrees Celsius. So first thing you will do, convert temperature to Kelvin. So 27 degrees Celsius equal to 300 Kelvin. The second thing you will do is to write a formula for pentavalent band gap. Okay. So what was the formula? I also forgot the formula. Just check it. Pentavalent band gap. So let's check the formula. Take this formula from here. For pentavalent band gap, you will have to use this formula. Okay. EF equal to. So let us take this formula. So you need to calculate EF minus EC equal to minus the value of K is given 8.62 into 10 to the power minus 5. Value of T is given into 300 into ln the NC, that is effective density of the conduction band, that is 2.82 into 10 to the power 19, and ND, that is 10 to the power 15. So after putting all these values, when you calculate, so you will get answer as 0.285. Okay. So the correct answer is answer B. So please see it how it has been done. Put the values, calculate it by yourself. You will get the answer. type of questions. So if there is any change in the question, or if there is any change in value, you can easily put these empirical relations, and you can calculate the values and get it done. So for this, the we have calculated it was 0.285. Okay, so the region where electrons and holes diffuse across the junction is called, so region where electron and holes actually diffuse. So this is like a semiconductor. So these are holes plus sign represented by these electrons. So this is the region in which they diffuse. This is called depletion region. Okay. So the correct answer is answer B. And how does this look like? This look like this. This is the depletion region. Okay. So a recombination of hole and uh, this electron pair happens in the depletion region. The maximum current provided by PV array when the output connectors are sorted together is called. So when the output connectors are sorted, like if we have two output connectors, okay, so let's say this is the point, this is the point. So we have two connectors, okay, and these two are sorted by joining them, touching them with each other. So what happens that there will be a short circuit current which will flow through it, okay. So it's basically short circuit current. So correct answer is answer A. Now a PV module of 36 solar cell with each solar cell having an area of 0.015 meter square. If the packing factor of the module is 0.8, the total area occupied by the module is, okay. So 36 into 0.15, okay. So this will comes out to be around 0.675 or something, okay. Now there is a question of Fermi level. Okay, so Fermi level dash when temperature increase and intrinsic semiconductor material. Actually, Fermi energy level when the temperature increase for intrinsic semiconductor material, the Fermi energy level actually changes its shape. So correct answer is C here. At a temperature of 0 Kelvin, the silicon behaves as insulator. Okay, all the semiconductors behave as insulator at 0 Kelvin. A solar cell has an open circuit voltage of 0.2, short circuit current of 5.5, okay, and maximum voltage of 0.125, maximum current of 3 milliampere. The fill factor of the cell is. So before this, I think, oh, sorry, this is not, this is 0.8 divided by 0.8. I just remembered. This is 0.675. So we need to calculate the fill factor, okay. So what is the formula of fill factor? It's V max into I max upon V open circuit into I short circuit. So maximum voltage of 0.125 into maximum current of 3. Mind the units. Units should be for above and down. The units should be same. Open circuit is zero point 0.2 and short circuit current is 5.5. So this comes out to be around 0.34. So the fill factor is A. So similarly, you can easily do these type of questions. Okay, so a PV source is given. Now you need to calculate the if MPPT is interposed between the source and load, and that is a power what will be given as. So when you calculate this, the answer will be 108. Okay, so I am not going in detail because these are basically these are formula based questions. Just put the values, you will get the answer. Okay. The time required by the system to operate in order to recover the cost of the MPPT. So when you put these values, these are joint question. Okay, the data is given here, so you need to uh, use the data of this question for solving this question also. So the correct answer for this is 5694. Okay. A solar cell area of 4 centimeters square receives solar radiation with photon energy this and intensity this. Measurements so open circuit voltage of 0.24, short circuit current of this, maximum current is this. The efficiency of solar cell is 1.1. The maximum voltage a cell can deliver is. Okay. So first thing is that ki VOC is given to you. Let me solve this. VOC is given 0.24. Now short circuit current is also given. How much is this? Short circuit current 10.24. And please mind the units. I'm not writing it here, but please mind the units. And how much is the maximum current? The maximum current is 6.5. How much is the efficiency of cell is 1.1%. Area is 4 centimeter square. So efficiency is basically now efficiency is V max into I max upon okay. So how much the intensity into area? The intensity 200 watt per meter square. So V max equal to now in you need to calculate this V max value. Okay. So efficiency is 1.1%, that is 0.011 into 200 into 4 into 10 to the power minus 4. Why 10 to the power minus 4? It's in watt per meter square. Area is in centimeter square. Upon 6.5 into 10 to the power minus 3. So Vmax comes out to be around 0.135 volt. The correct answer is A. Okay. The fill factor. So we have solved this fill factor question here also. Fill factor. Okay. So just put the values. The fill factor will come out to be around 0.357. Just put the values. So you know the Vmax, you know the Imax, you know the open circuit voltage in the last question, and you know the short circuit current. Okay. So just put it Vmax equal to 0.135. Okay. The data is given here 0.135. Okay. It's not given here. Yeah, we have calculated the Vmax here, na 0.135 into Imax is 6.5 as given in the previous question. See, it's given maximum current. Then V open circuit is given 0.24 and short circuit is given 10.24. When you put the values, it comes out to be around 0.357. Okay, the correct answer is answer B. Okay, so with this, I think we have discussed all the questions and solved almost all the questions. So this comes to the end of this live session 4. I hope you guys have practiced a lot of questions with me in this live session, and you guys must have enjoyed this live session. So even if there are any queries you want to ask, you can always write a mail to me on this email ID. Otherwise, I will suggest keep please put the question in discussion forum, because most of the people are also having problems, so they will get benefited from your question. So thank you all. We'll meet once again in the next Monday, on the next Monday, and we'll discuss the week 5 contents and the previous week assignment question of week 5. Okay. Thank you all once again. You can leave the meeting.